Hello, class. This is one of my favorite lectures really to do. It's, I think, one of the most important different analysis techniques to use. And in fact, I've always used this much more than nodal analysis. I don't really know anybody who really uses. I mean, no, we're going to need nodal analysis when we do an analysis of op amps, because the front end of an op amp has literally infinite resistance, so no current flows in there, and we're going to need nodal analysis to analyze that. But what I wanted to do with mesh analysis, this mesh analysis, is just get the procedure down. And in your book, it goes through steps on mesh analysis and what you how you would do mesh analysis. But like I said before, the way that they do the summation as they work through a mesh analysis loop, I'm just drawing the mesh analysis loops right now, and you'll notice that they have to be in the same direction, right? So I've got all the loops going in the same direction as I sum the various different voltage increases and decreases as I go through that loop. And that's what I want to do. First of all, I want to sum all of the voltages as I go through the loop. So let's make a procedure. So one, sum all voltage increases or decreases around the loop. See how mesh analysis takes advantage of Kirchhoff's voltage law, whereas nodal analysis takes advantage of Kirchhoff's current law, right? And that's basically what we're doing here now. We're trying to come up with two independent equations here that are going to relate to I1, because I'm going to call this I1, and this is loop I2, right? Should I really say I1 and because I'm going to use I1 and I2 in those. Let's just look at the, I forgot to put the voltage source for that one. No, I got it. 2 volts, 6 volts, 2 ohms, 4 ohms, 1 ohm. I'm going to do it with a very easy 2-loop circuit first, and then we're going to jump into a 3-loop where it's really much more beneficial. I mean, with this, we don't have to use matrices to solve this, really, do we? Although we could, and I probably will. But with the 3-loop circuit, you really have to use matrix operations to solve that. So let's just do a simple 2-loop, easily using substitution algebra to figure out what's going on here. So let's do a summation first of loop 1. I'll call this loop 1. I'll call this loop 2. So if we do an analysis, and I'm doing this, opposite, like I said before, I do it the conventional way. Your book sort of does it in an unconventional, everything that's positive is negative, everything that's negative is positive. The way I look at it is, if I have a minus here and I've got a plus here, I'm going from the negative side to the positive side. So that's an increase of 2 volts. And so that's how I sum it. So 2 volts, right? And then what have I got here as far as voltage? Doesn't V equal IR equals delta V, that voltage drop across the resistor? So I know that the voltage drop across the resistor is going to be IR, right? And that's a subtraction, because really I'm going from the plus to the minus here, so I'm losing voltage going across that 2 ohm resistor. And I know that my current in that is going to be I1, right? I said that I'll use I1 in this loop and I2 in this loop. So minus I1 times 2 ohms. That's a 2. And then let's go over to the 4 ohm now. Now minus, that's going to be a voltage drop across the 4 ohm, but there isn't just one current flowing through there, is there? No, there's one current that's flowing through that's I1, and there's another current flowing in the opposite direction called I2. So I now have I1 minus I2 times 4 ohms. Do we see any other voltage increases or decreases as we go around this loop? No. So we know that that has to equal 0, right? Now I'm just going to put this one next to it because it'll be easier for us to simplify as we're going down to get to that point. So let's do the second one as well. I'll start here just like I did last time. So I go up here, and the first one I run into is this 4 ohm resistor. Now, when I'm looking at it in this loop here, the I2 is going this way, isn't it? And the I1 is going this way. So this is going to be I2 minus I1. So when I do that thing, the first thing that I've got is minus 4 ohms times I2 minus I1. Now we go around the top, the only current flowing through the 1 ohm resistor, right, minus 1 ohm is just going to be I2, right? And now when we come down to the 6 volts, we're going opposite to the 6 volts, right? This is positive, that's negative. So instead of it being a positive 6 volts, it's going to be a minus 6 volts. And we know that that whole thing equals 0 volts, right? So we've got 2 equations now that both equal 0 volts. Why don't we solve these a little bit? So I've got, let's just do it with the 2 ohms, or with I1 first. So I get minus 2 ohms I1 minus 4 ohms I1. Can we take that minus 2 ohms and that minus 4 ohms I1 and throw it on the other side? Sure. You know, to make it a positive. So that would make it plus 4 plus 2 is 6 ohms I1, right? And then I'm going to put the 2 volts over on this side of the equation. So the 2 volts basically is staying on the left-hand side of the equal sign, and I'm taking this and bringing it over to the other side so it becomes a positive. I'm also going to do that. If you look at this, I've got a minus I2. So does that make it positive I2? Positive I2 over to the other side gives me minus 4 ohms I2. And all of that equals 2 volts. All right? We could put some parentheses, I guess, around the ohms there, right? So that we separate out the I2, and then we've got equals 2 volts. If I do the same thing for over here, getting I1, I2 all lined up, let's just put that line down there. Let's try this then. So I've got minus 4 ohms I2, minus 1 ohm I2. Why don't we take that over to the other side of the equation, and those minuses will become positives, right? And how about I1? What are we going to have for I1? Now I've got a minus 4 ohms times a minus I1. So doesn't that make it plus 4 ohms, right, times I1, and then minus, I'm just doing minus, so that I might have to do 2 steps here. I don't want to lose anybody. So I get 4 ohms I1 minus 4 ohms I2 minus 1 ohm I2. That gives me minus 5 ohms I2, right? And then what does that equal? Well, I think we can see I've kept all of the things on this side. So I've still got the positive, positive. I could take that 6 ohm, that minus 6, and bring it to the other side of the equation, which would give me a plus 6 volts. Does everybody see that? So now I've got 2 equations. 2 equations And I really have two unknowns too, don't I? I've got I1 and I2, two equations, two unknowns. Can't we just throw that into a matrix? Couldn't I say that I have 6 ohms minus 4 ohms, right? Let's put our solution column down there too, equals 2 volts. And I also have, if I go to this, I have 4 ohms. I1 minus 5 ohms I2. I probably wrote this wrong. Gives me 6 volts. Just want to make sure I've got this everything right. Minus 4 ohms. Yep, equals 2 volts. And I probably should have brought those over to the other side, making that a minus and that a plus, and that would be that would still be a minus, and you know, I could do that, but it comes out to the same thing either way. It's just two equations, two unknowns. I've got a matrix here. I've got my solution column to the matrix here. And of course, via, you know, the solution to a 2x2 matrix, and I'm just going to draw this up here, although I think everybody probably knows this, is A, B, C, D. If I want to find the determinant of that, that would be AD minus BC, right? Does everybody remember that? And if I had a 2x2 matrix like that, and I wanted to find out, if you don't know this, you should have learned this in math, but if you don't know this, if you wanted to find out what I1 and I2 are, is we can just actually replace I1's column with the solution column and find the determinant for that, divided by the determinant of the entire thing. So let's do the determinant. Let's find out what is the determinant of 6 minus 4, 4 minus 5, right? What's the determinant for that? So let's just work this out first. Again, we're going to use it for the 2 to find out I1 and I2, but we have to find this matrix first because this goes in the denominator. So if I use my equation I've got over here, A times D, so minus 30, right? So I'm finding the determinant of this 2x2 matrix. So minus 30 minus a minus 16, right? So minus 30 plus 16 gives me minus 14, right? Okay, so we know the determinant of that equals that. Now I also want to find out, I'll just put that there. I also want to find out, since I'm trying to find I1 then, because I1 is the first column, I would replace with my solutions column 2, 6, minus 4, minus 5. And I would divide that by the one I have here, 6 minus 4, 4 minus 5. Okay, and we know the answer to that already, but let's do the top. So I've got 2 times minus 5, which gives me minus 10, and then minus a minus 24. Does everyone see that? 6 times minus 4 is 24. I'll just put brackets around there. So I've got 24 minus 10, or 14. And on the bottom, I have minus 14, right? So I've got 14 over minus 14, which gives me minus 1 amp. Now let's do the other side. Let's do I2. So I2, all I would do is replace the second column with the solutions column. So that gives me 6, 4, 4, I don't really need that line or anything. I don't know why I put that line there. It almost makes it look like it's, there we go. Okay, so I've got 6 and 4, and then I'm going to replace the second column with the solutions column. And the solutions column is 2 and 6. And I divide it by the original one that we have, 6, I'll still put it down there, 6 minus 4, 4 minus 5, right? And so now I know the bottom is 14, is minus 14, right? But the top, 6 times 6 is 36. Let's put a 36, right? Minus 8. 36 minus 8 is 28. 28 divided by minus 14 is minus 2 amps. Now, I'm pretty sure that all of that's right, but I'm just going to put a line below that for a second. I'm just going to check something, and I want to get the other one. Hopefully we have enough time to do the 3x3, or at least start the 3x3. All right, class, I am back. I hope that everybody, I was just a minute or so. I just wanted to set up, oh, got the wrong pen. Oh my God, I left the top off it. I just wanted to set up our 3x3. Of course, this is very easy. 2x2 matrices are very easy. The introduction to mesh analysis is very easy. It becomes a little more difficult when we go from a 2x2 matrix to a 3x3 matrix. And I want to teach you a trick that I use in a 3x3 matrix too. So let me just draw this circuit first so that we can get started on our mesh analysis. This is, like I say, a 3-loop circuit rather than a 2-loop circuit. It's still not what I would call a really complicated circuit. You could probably, use your branch current methods to, work through something like this, although it would not be very straightforward. Whereas the mesh analysis method is very straightforward as far as the solution goes. We just sum the voltages going around the individual circles. I want to give you some numbers. That's 10 ohms. This is 8 ohms. This is 5 ohms. I could use realistic things. I just really want to show you now. When I give you tests or whatever, I certainly will use real numbers, not so much on home sets because those are out of the book, but on tests I'll use like 330 or 560 or but the standard. Now we know a couple of things. We know down here this is going to be equal to 0, right? And we know that this is 15 volts, so I know that right here I've got 15 volts, don't I? So I think everybody can see that we could still do some analysis, without extending into that. We could use other ways to find out certain aspects of this, but the easiest way, you also probably thought, hey, you drew these backwards, right? If you had drawn them the other way, this would have come out as positive 1 amp and positive 2 amps. Why'd you draw it this way? That's my convention. Right. As long as I'm drawing them all in the same direction, I could draw it counterclockwise, in all 3 of them, but I like to draw it clockwise. And that is pretty much the standard convention of most people. It doesn't matter which way you go around the circuit, just so long as you go in the same direction all the ways, or at least keep that all straight when you're working it out. I find that putting them all in the same direction is required, but I'm not sure what the reason is for that. I'd have to go into that and look at it. It's with all the other things going on in electrical engineering, that is a very minor aspect of what you'll do. In fact, you'll find out that a lot of what you'll be designing in the future is going to be things that you can just throw up on a simulator, and then that simulator also has a way to design a printed circuit board for you and a full layout of this printed circuit board, so that you could, make a small, very compact printed circuit board of the circuit that you wanted to do. That's the future. And I think that's going to be happening all over the place, and rationalization using designer software. All right, we're not at that point. You're not at that point yet. You're at this point. And this point is learning how to do mesh analysis on a 3-loop circuit. Let's start, right? Let's sort of start and just sort of see what we have here. Let's start with, I'll make that has got to be the easiest one of all. And then I'll call that number 2, and I'll call this loop 3. So let's go through our analysis of our 3 equations as we go around the loop. Now that's the minus side, that's the plus side. So the way that I sum that is I'm going to say that's 15 volts. I call that 15 volts, even though your text does it backwards. The standard convention is really to say that you're going from negative to positive. It's 15. Now I'm going to have a voltage drop here at 8, right? So I don't know how to stop that. Sorry, I'm not answering that, but it might just go on for a while. So let's look at the voltage drop that I've got right here. I'm going to call the, just a second. All right, class, I'm back. That was a friend of mine that's just going through a divorce and stuff. And so I thought, well, I better answer that phone before he tells me he's going to kill himself. I know many of you are not married. And I certainly hope that all of you are not divorced. So, that'll be friends that you meet in the future. I'm hopeful, and hopefully you'll never meet them. You'll never know anybody that's divorced or never get divorced yourself. So, having said that, I have set it up for 15 minutes again. And so let's do this 3-loop circuit that we've got here. So first thing we've got from the minus to the plus, I say is positive 15 volts. Let's do the 8 ohms now. Well, we got 2 currents flowing through, right? We've got I1 that's flowing that way, but we have I3 that's flowing that way. So minus 8 ohms, right, times I1 minus I3. I don't think I've lost anybody there. And then here, I think everybody can see that this is sharing the current of I1 flowing this way, and then I2 flowing that way. So they're flowing in opposite directions too. So it'd be I1 minus I2. So minus 3 ohms, I sub 1 minus I sub 2. All right. And then we've got the last one down here. We've got nothing. So that equals 0. Well, that's our first one that we've got right there. Now let's do the second one. Second one over here is I2. So if I start at the bottom again, I'm going to have minus 3 ohms, right? But now it's I2 minus I1. Right? Because I2 is going in that direction, but I1 is coming in the opposite direction. Same thing is true here. We've got I2 flowing that way, but we have I3 flowing this way. So it's another minus. It's going to be minus 5 ohms times I2 minus I3. And then the last one here, the 2 ohm, is just going to be minus 2 ohms, but the only thing that we have flowing through it is I2, right? And then all of that equals 0. That's 2 ohms. So that's 2 of our 3 equations. Those 2 of the 3 simultaneous equations. I know what you're saying to yourself right now. Oh my God, this is what I learned matrix determinants for. So solution of matrix in linear algebra. That's right. That's exactly what you learned it for. Let's do the third one now. Well, the third one, we're very similar to 2. We don't really have a voltage source in there at all, but we do have things that are falling. So I'll start out right here. So that would be minus, I'm going to try to give myself some room, minus 8 ohms, right? And then times I3 minus I1. And then I've got minus 10 ohms, right? And the only thing flowing through that is I3. And then with the 5 ohms, I've got minus 5 ohms. And the two currents flowing through that are I3 minus I2. I3 minus I2. And that all equals 0, right? So we've got 3 equations now. I want to simplify those 3 equations in terms so that I can put them into a 3x3 matrix. So let's do that with these. So the first thing I want is I1. Everything has got I1. So I've got minus 8 I1 minus 3 ohms I1. That's minus 11 ohms I1. So minus 11 ohms I1. How about I2? I've got minus 3 ohms, and then I've got minus I2. So that would be plus 3 ohms times I2, right? How about I3? Well, I have 8 ohms, minus 8 ohms times minus I3. So that gives me plus 8 ohms I3. And what does that equal? That equals, well, this is 15 volts, so it's going to be minus 15 volts because I've kept all those on the left-hand side, and I brought the 15 over to the right-hand side, so it becomes a negative, right? Now let's do the same thing I've got here. Now let's go through I1. So I've got plus 3 I1 plus, nope, that's it. So 3 ohms I1. How about I2? Well, I got 2 of them I have to do. I've got minus 5 I2 minus 3 I2, which gives me minus 8 ohms I2. Let's do I3. Oh, wait a second. It looks like I've left something out. Minus 2. That should be minus 10. I'm sorry about that. I forgot the 2 entirely. And then let's do 3. So that's going to be plus 5 ohms I3. And what does that equal? 0 still, right? Now let's do our last one down here. We want to do the same things. I1, I2, I3. So I've got 8 ohms I1. We can do this a bit faster, can't we? Because now I've got minus 5 times minus I2. So it's plus 5 ohms I2. And then I3 we have in all 3 of them. Minus 8, minus 10, that gives me minus 18, minus 5. That's minus 23, isn't it? So minus 23 I3 equals 0. All right? Now, let's make our I think we can use this either one. So I've got minus 11, 3, 8, minus 15. How about the next one? I've got 3, minus 10, 5, 0. Do the last one. 8, 5, minus 23, 0. All right. Does everybody see the 3x3 matrix that I've got? You know, let's just solve for that 3x3 matrix that I have there. I'm just going to put a little arrow there and say that minus 11, 3, 8, 3, minus 10, 5, 8, 5, minus 23, the determinant of that. Let's just let's see. I just want to make sure that I've got this right. Just let me check something. Yeah, everything's exactly right. But what I wanted to do was to show you how we would do this. That takes some time, but I'm going to actually do it anyway. Uh, the way I do this is I take this one right here, and then I multiply it by these two. In fact, I'd love to draw you a picture of how I'm going to do this. And I'm trying to find a spot on here. You know, I think I'm just going to have to write it down here. So if I have A, B, C, D, E, F, G, H, I in a 3x3 matrix, the way that I do that is I put another 2 rows. See how it's got A, D, G, B, E, H, C, F, I. I'm just going to get rid of that entirely. What I do is I always write another 2 rows, the 2 rows, the 2 original rows. A, D, G, B, E, H. This is how I do it. Now you're going to say, well, that's not how they taught us in math, and of course it's not, because mathematicians are such geniuses, right? But here's how I do it. So I circle the first one, and then I make that first. So I know it's A times E, F, H, I. Then I do plus, because I'm moving to the right, right? So I'm going to take another color pen here. I'll use the orange. So now it's B, right? And it's going to be this and this. So we can just add those instead of subtracting like they do in math, and that all makes it so confusing. We're just going to add them as we go across. So B, and now the matrix that we're using is F, D, I, G. F, D, I, G. By the way, students have come back to me and told me that this is a much easier way to make sure that you get the determinants for a 3x3 right. So I've had a great response with the way that I do it. Now with C, you see why I have now moved these over? Because C now is just going to use those, and it's still a plus. I don't have to transpose these like they teach you in math or anything, right? Makes it so hard. So it's D, E, G, H. And that equals the determinant of the A, B, C, D, E, F, G, H, I 3x3 matrix, right? Okay, so we can do the same thing here. If we wanted to find out what the determinant is, that would just be minus 11 times the minus 10, 5, 5, minus 23 matrix, plus, let's just keep moving it over, so it would be 3 times the matrix now. Now we come down here, right? It'd be 5, 3, minus 23, 8, right? So 5, 3, minus 23, 8. And then plus, let's do the last one, 8, right? And then 8 would just use these, 3, minus 10, 8, 5, right? So that's where we are with that. And we would solve each of those individually, and we would have the matrix for that. You know, I'm going to stop this here. I'm going to finish this up in the next lecture. We're almost done with this. And Super Mesh actually is a shorter lecture usually anyway. So I'm going to finish this up in the next lecture, and then we're also going to touch on Super Mesh, which is very similar to supernodal. All right. I've sort of run out of room a little bit here, but we're going to work this out. And I want this to be, you know, worked out in a little more detail. We've certainly introduced mesh analysis. We've certainly showing how it's going to extend into the third loop as well. We want to learn this so that, you know, 2, well, that's easy, and we can probably solve that without even using mesh analysis. But down here with 3, there's several different types of circuits where I really have to use mesh analysis. I can't use a current divider rule, KVL, KCL. That can't solve the problem. I've got to use mesh analysis. So I will see you in the next lecture. We'll finish up this example, and we'll also move on to super mesh analysis.